Hi everyone. In the previous lecture, we started with our discussion on the MOS amplifier design. We said before we design, or rather before we expect a MOS amplifier to give us an voltage amplification, we have to first bias the device. So we have to set a quiescent drain current, drain to source voltage, and a gate to source voltage. So that's biasing, and we saw how to do that taking few examples in the previous lectures. The next step in this process of amplifier design is to have an estimate of what is the voltage gain that we are going to design this amplifier for. So we need to actually estimate the voltage gain of this amplifier. So in this lecture, we will actually take one specific configuration of a MOS amplifier and try to estimate the important parameters of an amplifier. So we had already discussed an amplifier generally is a two-port device, which means it has 4 terminals, 2 terminals at the input and 2 terminals at the output. But we also discussed that in general, one terminal will be a common or a shared terminal between input and output. So you will have totally an amplifier is a 3-terminal device. We have an input terminal, an output terminal, and a common terminal. So before I proceed with discussing the MOS device, I'll also just briefly mention that most of the amplifying devices, whether it's BJT, MOSFET, a vacuum tube amplifier, all these amplifiers are nonlinear devices. So their transfer characteristics or nonlinear functions of the input, for example, the output quantities or nonlinear functions of the input voltages or currents. Now, because of which we can't precisely define a voltage gain which is independent of the input voltage. So what do I mean by that? So for example, if you have a linear system of this type, y equals ax, or rather let me write v naught equals a times vi. If the system is characterized by an equation like this, then the gain is simply a, and it is independent of what input voltage we apply. But now let's assume the system is of this type, where you have a vi plus b vi square. So it has a nonlinear dependence on the input voltage. When this happens, if you try finding the voltage gain, so which is if I do v naught upon vi, so if I take the ratio of v naught upon vi, you get a plus b vi. So it means the voltage gain here is also a function of the input voltage you apply. So that's a very distinguishing parameter of a distinguishing characteristic of a nonlinear amplifier. So your voltage gain and the parameters will depend upon the input voltage that you apply. So then how does one define voltage gain for an amplifier, for a nonlinear amplifier? So what we do is something we have already discussed briefly. Now let's assume what I've shown here is a nonlinear characteristic between the input and output. We are going to assume that we are applying small signals at the input. At the input terminal, I'm going to apply a small signal so that around that input operating point or the bias point, we are going to assume, we'll try to calculate the gain at that bias point and assume that that gain is going to remain constant for the small signals around that bias point. So what we are trying to estimate in this lecture is actually the small signal gain of an amplifier. So we have already discussed biasing in the previous lecture. After biasing an amplifier, around that bias point or the operating point, we will estimate the small signal gain, the incremental gain of this amplifier. And we are going to assume that to a first order, your amplifier, you can expect that as the gain of your amplifier. So generally it will be lower than that, but that you can treat somehow as the maximum gain this amplifier is going to give us. If your input signals are very small, then you will nearly get the same gain that you will predict from, that you will actually derive from a small signal or an incremental model. So in this lecture, so that's what we are going to do. We are going to estimate gains from an incremental or a small signal model. So coming back to this discussion where I discussed an amplifier generally can be seen as a 3-terminal device, one as an input, one as an output, and third as the common terminal. So by this definition, if you see a MOS device has 3 terminals, I can then define 6 possible amplifier configurations in which I can use a MOS device as an amplifier. So if I define one terminal, each terminal as a common terminal, so I can define source as common terminal, then drain and gate can be either input or output. So I'll have two such possibilities in each while defining each terminal as a common terminal. So therefore there are 3 terminals, so I can define 6 possible configurations, out of which we will see only 3 can be used as amplifiers. The other 3 are impractical configurations. So first I'll start with common source configuration. So wherein the source is the common terminal between the input and the output, and gate and drain can be input or output. In the first example that I've shown here, gate is an input, drain is an output. In the second case that I've shown here, gate is the output, drain is the input. Now this is, in the first case, if you see, the input voltage appears across the gate to source junction. It appears across the gate to source terminals, gate and source terminals. And we know a MOS device from its transfer characteristics, the drain current is proportional to the input gate to source voltage. It has some dependence, it has actually a nonlinear dependence, but it changes in proportion to the gate to source voltage. So therefore, for an amplifier, you need the output, either voltage or current, should vary in proportion to the input that's applied. Now in this example, since the input happens to be VGS, the output happens to be the drain current, then we know the drain current varies in proportion to the input. So therefore this amplifier, MOS device can be used as an amplifier in this configuration, with gate being the input, drain being the output. In the second case, on the other hand, when you vary, input is applied between drain and source terminals. If you vary the drain and source terminal, of course there will be small change in the drain current because of channel length modulation, but it will not induce any change in the gate current or the gate voltage, gate to source voltage. Only drain current is going to change because of channel length modulation, but that will not create any increase in the gate current or the gate to source voltage. So therefore this cannot be used as an amplifier. So generally the fundamental definition of an amplifier is some kind of an action at an electrical distance. Output port and input port, there is no direct electrical connection between the two, but if I excite the input either with voltage or current, either the output voltage or current should change in proportion to that. But in this case, in this configuration that I have shown here, neither of that happens. Neither the gate current nor the gate voltage will change by a change in the drain to source voltage. So therefore, this amplifier configuration has to be discarded. So this is what we refer to as the common source configuration. So how do we identify which is the common terminal? See where the input is and see where the output is. The third terminal is the common terminal. So this is called the common source configuration. I very briefly mentioned something here. So generally amplifiers amplify in one direction. So if you apply an input at the input port, the output will be in proportional to the input voltage, and amplification happens only in this direction. But if I apply an input at the output, so for example, if I apply an input at this terminal and expect to see some, I will probably not see any voltage in response to this input at the input terminal. So amplification doesn't happen in this direction. So generally amplification, it's a unidirectional amplification. It happens in one direction. This is generally true for most of the amplifier configurations. Only few amplifiers, which we will discuss later, will violate this. So it will have some kind of a weak amplification in the opposite direction as well. Okay. So now I have introduced very basics of common source amplifier. The next thing that we are going to do for an amplifier is, once you know an amplifier, fundamentally we will try to find out the important parameters of an amplifier. Those important parameters are the input resistance, Rin, the output resistance, and the intrinsic gain of an amplifier. These parameters help us in deriving a small signal model for this amplifier. From that small signal model, we can very accurately predict the total voltage gain that this amplifier can offer under loaded conditions. When I say loaded conditions, source has a finite source resistance and there is a finite load resistance. So an amplifier's gain, we will see, also depends upon what you connect at source and load. To estimate accurately how much will the gain decrease in the presence of loading, so when there is load and source resistances, it's helpful to have an estimate of all the three important parameters. So these three, the input resistance, output resistance, and the intrinsic gain or the unloaded gain, are three important parameters of any amplifier. So first, I'm going to find the intrinsic gain of this amplifier. The intrinsic gain or an unloaded gain of an amplifier is the maximum gain that this amplifier can give us. And that's measured by making the load resistance as infinity and the source resistance as 0. So the input is directly driving this amplifier without any source resistance. And at the output terminal, the load resistance, we are not loading the output with any load resistance. So the amplifier doesn't have to deliver any power to the load resistance. So now we will try to find what is the maximum attainable voltage gain for this amplifier. So first we can solve this intuitively, but first when we are doing it for the first time, we go by using the small signal models. So at the input terminal between gate and source, we saw in the previous lecture from the small signal model of a MOS device, the gate to source is an open circuit. For any finite gate to source voltage, the current drawn is 0. So it's an open circuit between gate and source. And between drain and source, we have a current GM VGS that's flowing from drain to source. But since VGS is equal to VI here, I have written the drain current as GM times VI, where GM is the transconductance which has to be estimated from the transfer characteristics. And we have also modeled the channel length modulation. So a resistance R0 is shown here, so which is estimated from the output characteristics. So which is incremental change in the drain to source voltage divided by the incremental change in the drain to source current. That's your R0. Now to find the voltage gain, you can directly apply Kirchhoff's current law at this node. So again, we'll apply this for the first time. After that, we'll try to analyze circuits intuitively. So the sum of the two currents, GMVI plus V0 by R0 is equal to 0. So that's what you get by applying Kirchhoff's current law here. So from that, you can directly get the voltage gain as V0 equals minus GM R0 into VI. You can also quickly intuitively solve this or visualize the circuit intuitively. You can see the circuit, there is a current GMVI flowing in this direction. Now I can also just reverse the direction of current and write it as minus GMVI flowing into R0. So the current minus GMVI flows through R0 and a voltage drop of GM minus GMVI into R0 is developed across R0, which is nothing but V0 itself. So you get the same expression V0 as minus GM R0 into VI. Now we will see what is this product GM R0 intrinsic gain dependent upon. So as a design engineer, can you vary this intrinsic gain by choosing appropriate W valves or an appropriate drain current? So I'll use the expression for GM, which is the root of 2 beta n ID. That's beta n here is W valve, mu n Cox W valve. So this is the expression for GM multiplied by 1 by lambda into ID. That's your expression for R0. When you take the product, the intrinsic gain becomes root of 2 beta n by ID multiplied by 1 by lambda. So now if you see here, the intrinsic gain here depends upon three parameters. One, it is inversely dependent on the drain current. If I keep every other parameter constant and just keep reducing drain current, this equation is telling us that the intrinsic gain should increase. Similarly, if I keep every other parameter constant, drain current, device length and all of that constant, and just increase the W valve ratio, if I just increase the W valve ratio, then I should expect an increase in the intrinsic gain. So here W valve ratio should increase, length itself should remain constant. So we can say an increase in the width. So A0 will increase in proportion to root of W valve. In the third case, it's also dependent on 1 by lambda. 1 by lambda is your channel length modulation parameter. So if you have a smaller channel length modulation parameter, you can expect a higher intrinsic gain. And we also discussed that this channel length modulation parameter lambda depends upon length, channel length. So it's actually longer the channel length, smaller will be your lambda. So longer the channel length, smaller will be your lambda. So if I want to have higher intrinsic gain, then I should choose a device with a greater device length. But we will see that at a later stage. I'll also talk very briefly about that right now as well. But we will see at a later stage that Of course, increasing the device length helps us in getting a larger intrinsic gain, but at the price of a reduced bandwidth. So we'll talk about that when we talk about frequency response of amplifiers. So here I have just discussed briefly what does this intrinsic gain depend upon: the drain current, the W-well ratio, and the channel length as well. So which is included in the channel length modulation parameter lambda. So I've shown here graphically how does the drain current vary, the intrinsic gain vary with the drain current. So for a given W-well, as I fix my beta n or W-well, as you reduce your drain current, you can see in this graph that the drain current just keeps increasing. The intrinsic gain just keeps increasing for reduced drain current. Similarly, shown here, for a given drain current, as you increase your W-well ratio or beta n, the intrinsic gain is also going to increase. So two things are happening here in both the graphs. In the first graph, if I talk about it, as I reduce my drain current, your GM is reducing, keeping everything else the same. GM is reducing, but your R0, because so your GM is proportional to root of ID. GM is reducing, but since R0 is proportional to 1 by ID, as I reduce ID, it's reducing at a much faster rate, increasing at a much faster rate, R0. So the product GM into R0, actually the product of GM into R0 increases with decreasing ID. Now whereas in this case, in the second case, what we are doing here is that drain current is fixed and channel length is also fixed, which means R0 is fixed. What we are doing here as you increase W-well is that we are increasing the transconductance of the device. So this equation is telling us that as you increase your W-well, your transconductance just increases, it just keeps increasing, so your intrinsic gain also keeps increasing. As per this equation, it's telling us that if I choose an exceedingly small drain current, I should get a really large intrinsic gain. For a given W-well, as per the first graph, it's telling us for an exceedingly small drain current, the intrinsic gain should be exceedingly high. Similarly, for a given drain current, as I keep increasing this W-well ratio to a really large value, your intrinsic gain should also increase significantly. But this will not be the case. In fact, we will very briefly discuss and show that it's going to saturate after it reaches a certain limiting value. But before that, I'll quickly make a comparison of BJT with a MOS device. We will try to compare the intrinsic gain of a bipolar junction transistor with that of a MOS device. So the equivalent to a common source configuration in MOS amplifier is a common emitter configuration in BJTs. So the emitter terminal here, if you see, emitter emits electrons and collector collects it. So you can similarly see that source emits all the electrons and drain collects it. So, and the gate terminal, the base terminal happens to be the control terminal here in BJT, and in MOSFET gate happens to be the control terminal, proportional to which the drain current varies. So therefore, for the equivalent to a common source will be a common emitter configuration in BJT. In a common emitter configuration, we had already derived the intrinsic gain happens to be minus GM into R0. And GM for a BJT, it's an exponential device. So if you remember, for a BJT, the characteristics of a BJT, the collector current is alpha times IS e power VBE by VT. So there is an exponential dependence of the input voltage on the output current. So therefore, if it is an exponential device, then the transconductance will be proportional to the quiescent collector current itself. Now transconductance, if you see, is ICQ by VT, that comes from the exponential characteristics, multiplied by R0, which is VA by ICQ. So the product is independent of the collector current. It only depends upon the ratio of VA by VT. Now this tells us a very interesting result. It's telling us that as a designer, you don't get to control the intrinsic gain of a BJT much. There is a fundamental limit given by VA upon VT, which is determined by the device parameters. So therefore, there isn't much control of the intrinsic gain in a bipolar junction transistor. There is a fundamental limit. But we just saw from the previous analysis that for a MOS device, on the other hand, the intrinsic gain is something that can be controlled by varying the design parameters like drain current or the W-well ratio. So then does this imply, for example, if I choose an exceedingly small drain current, the intrinsic gain is going to be much larger than that of a BJT. It can be really large. The intrinsic gain can be really large from this equation. I mean, if I choose drain current close to 0, then I should expect an infinite intrinsic gain. Does this mean a MOS device is better than BJT? If you recall in the previous lectures, I said when we compared BJT and MOSFET very briefly, we said a MOS device has a higher transconductance for the same drain current, for the same current. So meaning if I equate the collector current to the drain current, the quiescent drain current, if I choose the same currents, a BJT is going to offer you a higher transconductance. For the same collector current as that of a drain current of a MOSFET, BJT is going to give you a higher transconductance because that comes from the exponential versus square law characteristics. So if you see, the slope of the exponential graph is always going to be larger than any polynomial, a simple polynomial expression. So therefore, we can argue that to a good extent, the transconductance of a BJT will be higher than the transconductance of a MOS device for the same currents. So then, but here for us this equation, we are seeing that the intrinsic gain is much higher in a MOSFET. It can be designed to be much higher in the MOSFET. But in reality, what happens is that as you keep increasing, or for example, let me speak about the variation of drain current, intrinsic gain with drain current, as you keep reducing the drain current, as per the equation, we said that it's going to increase indefinitely. But after a certain value of the drain current, the intrinsic gain is going to saturate to a limiting value. In the same way, for a given drain current, as you keep increasing W-well ratio, after a certain value of W-well, the intrinsic gain is going to saturate, and this value will be same. So let's call that A max here, and this will also be A max. This is the maximum gain and it's going to saturate. The question is, why does it saturate? So to understand that, we will look at the MOSFET again, the structure of a MOS again, and we have to see what exactly happens as you keep reducing drain current or increasing W-well. As you keep reducing, or let me first talk about reducing drain current for a given W-well, what is happening is that the drain current is given by beta n by 2 into Vgs minus Vtn the whole square. So as I increase beta n, since the drain current is fixed, your Vgs is going to reduce. Eventually when beta n becomes really large, your Vgs is going to approach Vtn. Now under that condition, your device will no longer be in the strong inversion condition. So we have derived all these equations, the equations for the drain current of a MOSFET, under the assumption that the MOS device is in strong inversion. The surface electron concentration is much higher, or rather it's as high as the bulk hole concentration. But now when your Vgs comes very close to Vtn, that condition will no longer be true. When that condition is no longer true, we can no longer use the square law characteristics of a MOS device. The characteristics will not go into the details of it, but the drain current will now start having an exponential dependence on the gate to source voltage. How does that happen? One can intuitively see here, there is a PNP transistor, N plus being drain, so the emitter being the source. A parasitic PNP transistor, an NPN transistor is automatically formed in a MOS structure. Now normally what happens is that the surface region where there is conduction in strong inversion will be populated by electrons. So there is no active base region, there is no such base region. But when your VGS is close to Vtn or smaller than Vtn or near Vtn, the surface is not fully inverted. So it will still behave like a weak P region. So there I have shown here in a pictorial way how it will look like a MOS device. So therefore, how it will look like a bipolar junction transistor device. A MOS device near the surface, you can see a parasitic BJT structure there. And this junction, generally drain terminal will be higher than the channel voltage. So we can see this junction will be reverse biased. Similarly, I can argue that the channel voltage will be slightly higher than especially the surface voltage here will be slightly higher than the source voltage. So you can see that this junction will be forward biased. So we have an active region BJT present there. So we can see that the collector current then will have an exponential dependence on the voltage across the PN junction, which happens to be VGS minus VTN. Okay, so we can see some voltage drops across the oxide and the remaining voltage falls across the surface to source terminal. I'm not going into the details. We can say it's proportional to e power VGS minus VTN by VT. When your drain current satisfies this condition, then we just discussed for a BJT device, whenever your current or the output current is exponentially dependent on the input voltage, the transconductance is now going to be proportional to the drain current. Instead of square root of ID, it's going to be proportional to the drain current. When that happens, then your R0 is inversely proportional to the drain current. The product of GM into R0 will attain a limiting value. And that will be the value A max here. So that's what I've shown here in this graph. After a certain value of drain current, smaller value of drain current, when you approach this condition of subthreshold conduction or weak inversion. So where the channel electron concentration is not as high as it used to be under strong inversion assumptions. In that case, the square law characteristics will no longer hold true and the MOS will enter into a region of operation called the subthreshold conduction. In that region, your GM will be proportional to the drain current, so the product of GM and R0 will attain a limiting value. In the same way, in this graph, as you see here, as you increase your W by L ratios, your VGS will keep reducing, and as VGS reduces and approaches VT, the device will again enter into subthreshold region. So when it enters into subthreshold region, you will attain, the gain will no longer increase, it will attain a limiting value. So that's what we have inferred from this equations. So what I was trying to say is that if your device is in saturation and you have biased the device with some W by L ratio here, then of course as you keep increasing W by L ratio, initially you will see an increase in the intrinsic gain. But after a point you will not see that. It will saturate. It will not diverge to infinity as the equations predicted previously. In the same way, if you see here, the intrinsic gain for reduced drain currents will not diverge to infinity as well. It will attain a limiting value. And that limiting value, we gave an intuitive reasoning. Why does that happen? Because your MOS device enters into subthreshold conduction. Throughout this course, we will not go for subthreshold conduction. We will be using only these equations, which is the square law characteristics or the strong inversion assumption throughout the course. So I have just presented this just to give you an understanding. Probably in an advanced course, we will go more deeper into this. So finally, the one parameter which we have not discussed so far is the dependence of intrinsic gain on lambda, which is your channel length modulation parameter. A smaller lambda translates to higher intrinsic gain. And we know that the lambda, it's a the channel length modulation parameter depends on the channel length. If you increase your channel length, then we can expect to have a smaller variation in the drain current. So that's an increase in R0. So one can directly see that A0 is proportional to the device length, because your R0 increases as your channel length increases. For the same change in the drain to source voltage, you will see a smaller change in the drain current. So that says an increase in R0. So for the same change in VDS, you will now see a smaller change in the drain current. So that increases the ratio, which is nothing but R0. So your intrinsic gain does increase by increasing device length, but now there is a problem. As you increase the device length, of course the area of the device increases, because you have to keep your W by L ratio constant to maintain overdrive voltages to be same and all of that. So the area of device increases. The more serious problem is reduction in the device bandwidth, the maximum speed at which the device can operate. We will talk about that in more detail when we go to frequency response of MOS amplifiers. So that's it about the intrinsic gain of MOS amplifier. The next thing we are going to discuss is the input and output resistance of the MOS amplifier, of common source amplifier. So I said these are the three important parameters. With the knowledge of that, you can predict the gain, estimate the small signal gain for any load and source resistances. So before we go analyzing the equivalent resistance of a MOS device, what we will do is we will look at a MOS device from three different nodes and see what impedance does we see from all those three different nodes of a MOS device. So first, when I'm looking at one specific node, I'm going to short circuit the other two nodes. So if I'm going to look at the gate, I'm going to short circuit drain and source. And if I'm finding the impedance looking into this node, into this terminal, what am I doing here is I'm trying to find the impedance with respect to this terminal and an AC terminal, AC ground terminal. Okay, the equivalent resistance perceived if you apply a voltage source and measure the current. So the equivalent impedance perceived by this voltage source at this node is what I'm calling as resistance looking into that node. So now I've shorted the other two nodes, drain and source are shorted, and now I'm going to apply a finite gate to source voltage. If I apply a finite gate to source voltage, you can expect some kind of a drain current flowing. Okay, so this is AC ground, so maybe you can expect some small drain current variations in the MOS device. But the gate current is going to be zero because your gate is an oxide. An oxide is an insulator. So for lower frequencies, we can say that it's going to behave like an open circuit. It's not going to conduct any current. So even though I applied a small VGS, delta VGS upon delta IG, or in fact IG itself is zero, there will be no change in the gate current. So this ratio is going to be infinity. So the input resistance, as I see at the gate terminal, is going to be infinity. So that's what I've written here. There will be no change in the gate current with respect to VGS. So I wrote dou IG by dou VGS, the whole inverse, which is your input resistance, is infinity. In fact, it's not very difficult to see that even if I open circuit the drain terminal, or connect it to some resistor here, the input resistance will still be infinity. Okay, because the input current will always be zero. There will be some output current at the drain terminal, but the input current IG will always be zero. So therefore, the input resistance will be infinity even if you connect some resistance at the drain terminal instead of just grounding it. The second case is looking into the source terminal. I am now going to look into the source terminal by grounding the drain and gate terminals. So the source terminal, I am interested in finding the impedance seen at this point. So again, I am going to apply a node voltage Vx, a voltage Vx at this node, so with respect to some AC ground, and measure the current Ix drawn by this MOS device. First, I'll ignore channel length modulations. R0 is ignored. If you ignore R0, if you see Vx here, Vx is simply nothing but minus of Vgs. So Vgs is, this is gate and this is source. So Vgs will be this voltage minus the source voltage. So Vgs will be minus Vx. So I can write Vgs as minus Vx and Id as minus Ix. So drain current flows from drain to source. So Ix is minus of Id. So if I take the ratio of Vx by Ix, that will be minus Vgs by minus Id. That will simply be equal to Vgs upon Id. So the incremental change I'm applying an incremental change in the gate to source voltage and measure the incremental change in the drain current. This is nothing but dou Id by dou Vgs the whole inverse. That's nothing but your transconductance. Okay, so inverse of transconductance. So dou Id, a change in, see what am I measuring here? I am measuring the change in the drain current or the Ix for a change in the input voltage. And since the input voltage happens to be Vgs and the current of interest happens to be the drain current, delta I, so dou Id, the change in the drain current with respect to the change in the gate to source voltage, is same as dou Ix by dou Vx. And this ratio is actually equal to Gm. So if you take the inverse of it, that's the input resistance, which is Vx by Ix, which will be 1 by Gm. So if I look into the source terminal with the other two terminals grounded, the impedance that I am going to see is 1 by Gm. So this is a different way of drawing the same circuit. I have just shown in both cases it's going to be 1 by Gm. Now what happens when I include R0? When I include R0, in this MOS device, now there are two paths for current. There are two currents that are flowing in this device. One is the drain current, which is the GMVX. This current is purely in response to the VGS. Then the second current that's flowing in the circuit will be due to the drain to source voltage variation. So now if you see here, drain voltage is at ground, VD is at 0, Vs is at Vx. So I can write Vx is also equal to minus VDS. Because drain, if you subtract the drain to source voltage, this entire voltage will be Vx, which is minus of VDS. So now there are two currents flowing. Your Ix, which is the current flowing from the input here, the current which is flowing from the input here will have two components. One is GMVX, which is the MOS device current, which is flowing through this device. The other current is Vx by R0. So that's what I've written here. So I can write Vx by 1 by Gm plus Vx by R0. You get this is nothing but the parallel of these two resistances, 1 by Gm parallel R0. So R0, if I include it, it's just going to come in parallel with it. Now, one of you had asked in the previous lecture, in this example, what we are seeing is that the source voltage seems to be at a higher voltage than the gate voltage. Will the device work? So you have to keep in mind, again, it's a very simple doubt, but since you're learning it for the first time, it's natural to get such doubts. What you are seeing here is that this is the small signal AC model. In reality, there is a DC voltage that's applied at the gate terminal, I am showing here, and there is a DC voltage applied at the source terminal, and there is a small signal voltage imposed on top of it, and similarly on gate as well. Now it will always be ensured for this, because this device has to operate in saturation even when there are small signals riding on top of the individual nodes. The sum of VG plus VG here is the DC gate voltage plus the small signal voltage, should be greater than the source voltage by at least VTN. So it will be greater than Vs plus the DC voltage plus the AC voltage plus VTN. Only then the device will conduct. We need the device to be in saturation under all throughout the range of the input voltage. Okay, so what I have shown here is, graphically I have shown here, even though there is a small signal VGS which is changing. So here if you see, there is a quiescent DC VGS, on top of it there is a small signal variation. So here VGS is positive, so source voltage is still lower than the gate voltage, small signal wise. But on the other cycle, the source voltage is smaller than the gate voltage. But still, if you see, VGS is still positive. So you will get, and it's greater than VT, so you will get some finite drain current in response to that. What we are drawing here, of course, this is your quiescent drain current. Your drain current is going to reduce, so I can model that as a reduction in the small signal current. Okay, so which is what I have shown as GMVX here. So in an actual circuit, there will be a drain current flowing from drain to source. So that will be the quiescent drain current minus GM times Vx. So that's why in this figure I have shown the drain current flowing from source to drain. Okay. So that if you see from drain to source, that current will be IDQ minus GMVx. So that's it. I'll just go back to the other and the final output resistance looking into the node. I'm going to look into the drain terminal by short circuiting the gate and source terminals. So I'm left, the final one is I'm going to look at the drain terminal by short circuiting gate and source terminals. Now when I short circuit gate and source, VGS is 0, small signal VGS is 0. Because small signal VGS is 0, you can picturize a current GM times VGS flowing from drain to source. That current will be 0. So you will be left with, if you draw the small signal model, which is what I have shown here, you will be left with only a resistance R0 between drain and source. So if you apply a voltage Vx and measure the current Ix, the ratio will simply be R0 itself. So you can directly see what is Vx. Vx is VDS. This is the drain to source voltage. And Ix happens to be the incremental drain current. So if you are going to apply a delta VDS and see an incremental current change, drain current change, this will simply be equal to R0 itself. That's the definition of R0. Incremental change in the drain current for an incremental change in the drain to source voltage, provided there is no change in the gate to source voltage. VGS is 0. Okay, so in fact, even if you apply some fixed voltage between drain and source, this is going to hold true. Or even if you connect a finite resistance at the gate terminal, you will still see a resistance of R0 at the drain terminal. So now we have all the three, now we have analyzed resistances seen at all the three terminals. So we are at a position to find out the important parameters of a common source amplifier. So now you are looking at this, the common source amplifier. Intrinsic gain we just derived some time ago, which is minus of GM or naught. The input resistance is Rn, which is infinity. The output resistance here, you're looking into the drain, source is ground, and so it's going to be R out. We just derived how to find the resistance looking into the drain. The intrinsic gain is minus GM or naught. Now one can intuitively see this way. I'll probably analyze one circuit and then come back to the intuitions. So if you see, look at this circuit here. Now I have loaded the amplifier, meaning I have applied a finite source resistance and a finite load resistance. And now we will see what happens to the voltage gain. Without any of this, when Rs was 0 and RL was infinity, we said that the gain was minus GM or naught. We will now see what happens to this value. Will it be lesser than this or higher than this? So first I've replaced this MOS device by its equivalent small signal model. Again, since we are doing it for the first time, we will do this. Next time onwards, we can directly analyze it intuitively. So replace this MOS device. Between gate and source there is an open circuit. Since the input resistance is infinity, the gate current will always be 0. If the gate current is 0, there will be no voltage drop across Rs. So the entire Vs will drop across the gate to source of MOSFET. So meaning Vs will be equal to Vgs. So from the small signal model, between drain and source, a current of value Gm Vgs will be flowing. But since Vgs equals Vs, I can say a current of value Gm Vs is going to flow from drain to source. And we have R0, which will entirely appear in parallel with the load resistance. So the small signal AC gain for this amplifier is simply going to be, I can club R0 and RL together and write it as R0 parallel RL. This resistance, I can write it as R0 parallel RL, and you have a current of value minus GMVS flowing in this direction. So when it flows across the resistance R0 parallel RL, I am going to get a voltage drop of minus of GM into R0 parallel RL times Vs. So I am going to expand R0 parallel RL, so which is R0 RL by R0 plus RL. You can write it as minus GM R0 into a factor which is RL by RL plus R0. So what you see from this expression is that the gain is now reduced when you start adding the load. So that's because of loading. When you load an amplifier, which means when you add a finite source resistance and a load resistance, the gain is indeed going to reduce. And by how much it's going to reduce, it's given here, which is RL by RL plus R0. And interestingly, if you notice here that there is no dependence on the source resistance, which means whatever be the value of source resistance, this gain is going to be unchanged. And that happens because your Rin is infinity. If your input resistance is infinity, it approaches the behavior of an ideal amplifier, voltage amplifier. Then the gain will be independent of source resistance. But because the output resistance is not infinity, so you are going to have some kind of dependence on the load resistance. And the dependence here is given by RL by RL plus R0. So now, if you want to maximize the voltage gain, then the value of load resistance should be in the order of R0. So typically when you see integrated circuit MOS amplifiers, common source MOS amplifiers, when they are used in op amps and other circuits, if you are going to use a common source amplifier, we will try and ensure that the load resistance which is connected to is in the order of R0 or greater than R0. Okay, because only then you get a good gain out of a common source amplifier. If you are going to design a common source amplifier to get maximum gain out of it, then the load resistance has to be large. What happens when the load resistance is very small? Meaning when RL is much smaller than R0, R0 parallel RL can be approximated to RL itself. So the gain becomes minus GM RL. So now if you see minus the gain, if you expanded GM in terms of the drain current and WL, you get an expression root of IDQ beta n into RL. So now if you see your GM, your intrinsic gain, the gain, loaded gain does have a dependence on the drain current and the WL ratios. So now you can see that if by increasing the drain current, you can actually increase the voltage gain. Okay, so that's what this equation is telling us. I mean, again, it doesn't mean that if I keep increasing my drain current indefinitely or W by L ratios indefinitely will the gain increase, but eventually what will happen is after some point your device will enter subthreshold or your R0 will start coming into the picture. Your R0 will start becoming smaller and smaller with increasing drain current. When that happens, it will get smaller and smaller. Eventually, no matter what you do, you can never exceed GMR0, minus of GMR0. That's the intrinsic gain of a common source amplifier. That's the limiting value. So if I plot your intrinsic gain as a function of the load resistance, if RL is 0, your gain, the gain as a function of load resistance, if RL is 0, the gain is 0, and eventually it will reach a limiting value given by minus of GMR0. I mean, I'm plotting only magnitude here, so it will be GMR0. It will increase first with increasing RL, but eventually it will reach a limiting value of GMR0. You can never exceed this value in a common source amplifier. So that's it. I'll just mention one more point which I forgot to mention. One of you had asked me can you assume a BJT and a MOSFET as similar devices with just one assumption that beta, if I assume beta of a BJT as infinity, can I say MOS and BJT are equivalent devices? The answer to that question is no. We can't directly assume that they are equivalent devices. See, they are two different devices from device physics point of view. They operate very differently. A bipolar junction transistor, the collector current in a BJT is because of diffusion of minority carriers in the base region. Whereas in a MOSFET, it's because of drift of surface electrons in near the surface. So the behavior, the physics is very different. I mean, I'm talking about strong inversion. It's very different. But we can make a comparison under small signal conditions. Once you apply very small signals and draw an equivalent small signal model for a BJT, the small signal model, the pi model, looks very similar to that of a MOSFET. In fact, it looks exactly the same as that of a MOSFET, at least for the output terminal is concerned. Now, these two models are equivalent if I make this assumption beta tending to infinity. If beta is infinity, then the base current becomes 0, small signal base current, and the gate current is 0 to begin with in a MOSFET. Then, if beta is infinity in a BJT, R pi tends to infinity, then I can say these two models are equivalent. So they are equivalent from a small signal sense. I can draw equivalence between the two devices, but the equivalence is in the small signal models. So that's the only point I wanted to clear. In the next lecture, I'll solve few problems on common source amplifiers, and we'll finish common source amplifiers after that.